Hello my dears, in this lecture I'll brief you the interesting concept of pseudo force. Before I proceed further, let me brief you regarding frame of reference. A system of coordinate axis attached to an observer having a clock is called a frame of reference. A frame of reference is basically of two types. One is inertial frame of reference and the other is non-inertial frame of reference. An inertial frame of reference is that frame of reference in which Newton's first law is valid. A non-inertial frame of reference is that frame of reference in which Newton's first law is not valid. And what is Newton's first law? Newton's first law says that A vector equal to 0 if and only if F vector equal to 0. It means that if you are operating from an inertial frame of reference and you observe that the vector sum of all the forces acting on the particle is 0, then you can safely conclude that the acceleration of the body is also 0. The reverse is also true. That is, if you find that the acceleration of a body is 0, then you can safely conclude that the vector sum of all the forces acting on the particle or the body will be also 0. Now, in a non-inertial frame of reference, this Newton's first law won't be valid. That is, if you are operating in a non-inertial frame of reference and you find that the net force acting on a body or a particle is 0, then you cannot conclude that the acceleration of the body is 0. And the reverse is also true. Now, let us come to the second law. Newton's second law says that if acceleration is measured from an inertial frame of reference, remember, Newton's second law is valid only for inertial frame of reference. I repeat, it says that if acceleration is measured from an inertial frame of reference, then it is equal to the vector sum of all the forces acting on the particle divided by the mass of the particle, isn't it? So remember, Newton's second law cannot be directly applied in a non-inertial frame of reference. Now, with this basic information, let us consider a situation in which we are having an inertial frame and we are having a non-inertial frame. Since non-inertial frame is an accelerated frame of reference, so let us say the acceleration of this non-inertial frame with respect to this inertial frame is, say, a naught vector. Now, let us consider a particle P moving with acceleration A with respect to this non-inertial frame as dashed. We are interested in finding out this acceleration A of this particle P with respect to this non-inertial frame of reference as dashed. Naturally, we cannot apply Newton's second law directly in this non-inertial frame. So, we go for vector analysis. We are supposed to find acceleration of particle P with respect to s dashed. So, I write a vector equation here. This must be equal to acceleration of particle P with respect to s plus acceleration of s with respect to s dashed. This is a simple vector equation, isn't it? Now, acceleration of particle P with respect to s dash we have taken as a vector. So we write it here, a vector, isn't it? This we leave like this right now, plus acceleration of s with respect to s dash we have written here. But what we have got is acceleration of s dash with respect to s. So we have to change the direction. So we incorporate a negative sign here, and now we can comfortably write acceleration of s dash with respect to s, isn't it? The negative sign simply indicates the change of direction, nothing else. Now, again, this implies a vector equal to a acceleration of p with respect to s minus s dash s, that is we are having here as a naught, so minus a naught vector, isn't it? Now have a careful look here. This we are going to multiply by m both sides, so m a ps minus m a naught vector, isn't it? Now have a look here again. Here you are having the mass of the particle multiplied by acceleration of particle p with respect to s. Acceleration of particle p with respect to s is this, isn't it? Means you are calculating this acceleration with respect to the inertial frame of reference. So second law holds good here. So here you can comfortably say that this must be equal to the net force acting on this particle minus ma naught, and this side we are having ma vector as before. Okay, now so a vector, from here we get f vector minus ma naught vector divided by m. You can write this equation as a vector equal to f vector plus ma naught vector with a negative sign naturally divided by m. Now have a careful look on this equation and put on your thinking cap. Now try to think. If this acceleration a naught is 0, means this s dash now becomes an inertial frame of reference. That is, either this s dash is stationary or it is moving with uniform velocity with respect to s. In that case, this a naught is 0 and naturally this term vanishes, minus ma naught. So you are left with a vector equal to f vector by m, which is Newton's second law of motion, isn't it? Here lies the trick. It means if you wish to apply Newton's second law in a non-inertial frame of reference, then you must have a force whose magnitude is equal to ma naught, isn't it? And add that force to all other forces acting on the particle, and this force will be acting opposite to the direction in which the frame of reference is accelerating, isn't it? This minus sign indicates that only. This ma naught, rather minus ma naught, is called pseudo force. Okay? Means whenever we are trying to apply Newton's second law of motion in a non-inertial frame of reference, we must take care of this factor, which is minus ma naught vector. While drawing the free body diagram, we will mark this force also with the magnitude m, which will be the mass of the particle, and a naught vector is the magnitude of acceleration of the non-inertial frame of reference. Naturally, we will mark this force opposite in the direction in which the frame of reference will be moving. See, how simple is it, isn't it? Now, let us apply this knowledge to a real life situation, that is in a numerical. Let us say we have an elevator which is accelerating upwards, say with a direct acceleration a naught. This elevator or lift is having an inclined base, and here you are having a particle or a small block which is sliding down on its own with an acceleration, say a. Let us say this length is given as L and this angle as theta, and we are supposed to find this acceleration a. Let me try to complicate it slightly. Let us find out the distance covered also, distance covered, and the time taken by this particle to reach the bottom. So we are supposed to find time also, isn't it? Now let us draw the free body diagram of this block or this particle. So it will be like this. So let us say this angle is theta, isn't it? What you can see that if the particle or the block is having a mass m, then its weight will be acting vertically downwards. The normal reaction force will be acting perpendicular to the incline, say r, isn't it? Now, as such, you are unable to see any other force operating here. But remember, since you are operating in a non-inertial frame of reference, because this elevator is accelerating with an acceleration a naught upwards, so we must include this pseudo force here, isn't it? The magnitude of the pseudo force is mass of the particle, let us say, which is m here, and the acceleration, here also we have taken a naught, so no problem, but this pseudo force must be marked opposite to the direction in which the elevator is moving, isn't it? So elevator is moving upwards, so you mark this pseudo force ma naught here. Okay. Now take the components along the incline of these two forces. Naturally, this angle is theta, this angle is 90, so this angle is definitely 90 minus theta, isn't it? So the components will be mg cos 90 minus theta, which gives you mg sin theta, plus ma naught cos 90 minus theta, which is again sin theta. This must be equal to the product of mass of this particle or the block multiplied by its acceleration, isn't it? So ma, isn't it? So you cancel out m here. So naturally you are getting a equal to, we can take sin theta common. So we are having g plus a naught sin theta. So this is the acceleration which we have found out, isn't it? Now regarding the length, this is L, this angle is theta, you are having a right angle triangle here, isn't it? So definitely this is L by cos theta, as simple as that. Now if you wish to find the time taken by the particle or the block to reach bottom, naturally we need an equation which relates distance, time and acceleration, and that is s equal to ut plus half at square, isn't it? Now see, this block or the particle is sliding on its own, so naturally its initial velocity is 0. So the expression now reduces to half at square. Distance covered is L by cos theta. So we put L by cos theta here. This is equal to half. Acceleration we have already found out. That is g plus a naught sin theta into t square. Or this implies t square equal to, we take this here, so 2L divided by g plus a naught sin theta into cos theta. Naturally, t you are getting as 2L by g plus a naught sin theta cos theta to the power half. See? Isn't it? So, like this you can find out the time also. Now, remember, if you are appearing for a competition, then chances are most likely that you are going to get a numerical in which you will be supposed to work in a non-inertial frame of reference. I am sure now you are not going to miss it. Will you? I don't think so.